What we saw previously was the indefinite integral where you do not specify limits of integration. Now I'm writing down the formula for the definite integral where I have an a and I have a b and my x is going between that. And I've chosen to write it down in sort of its fullest form where I'm not using any shorthand and I'm using f of x times g prime of x. And the big thing to note is that you just evaluate between the a and the b everywhere, but in particular, when it comes to that f times g, it's f times g evaluated sign between the a and the b. And then the integrals, of course, are evaluated between the a and b as well. But you use a different symbology for when its function's being evaluated and whether you're integrating between two different values. Regardless, this is what happens when you go and write down the definite integral. Okay, let's see how this works in a specific example. This is kind of a tricky example. First thing I want to note is we know the derivative of arctan of x, 1 over 1 plus x squared. But we do not know the antiderivative of arctan of x. We never saw that back in Calculus 1. How do I do it? It's not immediately clear to me. And it doesn't even look like a product. So if integration by parts is in some sense undoing the product rule, well, there's not two different things here, but there is, in disguise. This really looks like the function 1 multiplied by the function arctan of x. So I can set a u and I can set a dv. I'm going to set my u to be the arctan because I can take the derivative of that. I know the derivative of arctan, 1 over 1 plus x squared. And then the dv is just going to be the dx part. Okay, let me write that down over here just so I have it written down. I've got my u, I've got my dv. I now need to figure out the other thing. So my du is, well, the derivative of arctan, 1 over 1 plus x squared times the dx. And then the antiderivative, if dv is equal to dx, then v is just equal to the value of x. Okay, so we've got that values. Let's go and plug it into our formula here. We are using the definite formula now. I've got the integral from 0 all the way up to the 1, and I put it into my uv minus v du format. A couple different complicated things about this. First up, we had to figure out how to deal with the arctan portion, and then we had to do this integral. The integral takes a couple steps as well. So let's think about just the arctan first. For arctan, I'm trying to figure out arctan of 1 and arctan of 0. For this, you need to know special triangles. And the special triangle that's relevant here is the so-called 1, 1, root 2 triangle. This says that tangent of pi over 4 is 1 over 1, which is just 1. So if tan of pi over 4 is 1, then arctan of 1 is just pi over 4. So this special triangle allows me to evaluate arctan of 1 is just pi over 4, and so I can replace out what's going to happen to this left portion. It's going to be x equal to 1 times this pi over 4, and then 0. And by the way, arctan of 0 is 0 as well. Now, I had to figure out the integral. That's the next portion. I have to go and do this thing. So let me clear up a little bit of space, and I'm just going to focus just on that. How do I solve this? Now, you might recall from Calculus 1, this is a u substitution problem. I'll leave the link to a video that introduces u substitution right there. So if you're a little bit shaky with u subs, go and check that out. Now, for this u sub, I see I have this kind of messy denominator, 1 plus x squared. And the derivative of that denominator, which would be 2x, well, there is an x in the numerator. So not the 2, but I don't have to worry about that so much. But I've got the x. So this is going to be just a standard u sub problem like you could have had in Calculus 1. Let's run through it. I'm setting u to be my denominator here, the 1 plus x squared. My du is 2x dx. I also had to figure out where my 0 and 1 are going to transform to. If I've transformed with a u substitution, my limits of integration come along with them. So plugging in the value of 0 in for x, I get u of 0 is equal to 1 plus 0. Plugging the value of 1 in for x, I get 1 plus 1 squared, so 2. So indeed, my 0 and 1 transform to 1 and 2. Plugging all of that into my u substitution, I get the integral from 1 to 2 of 1/2. Notice that the du is 2x dx, and there's no 2 there, so I have to have this factor of 1/2. So 1/2 times du divided by u. The integral of 1 over u, may you recall, is just the natural logarithm of the absolute value of u, so it's 1/2 the natural logarithm absolute value of u evaluated between 1 and 2. Log of 1 is 0, so this is just going to be the value of log of 2 times that value of a half, 1/2 log 2. By the way, I can get rid of my absolute value signs when I realize 2 is a positive number, doesn't matter. Okay, so that was the other piece of information. So where were we? That was this integral we were trying to compute there. We'd already figured out the arctan portion. It was the pi over 4. Now I plug in this little value that we have, and that's it. That is our answer. Now, I really like this example because while it had many different moving parts, parts that you should pause the video and refer back to and make sure make sense in your head, there was the fact that it was a definite integral. It was sort of a weird choice of this integration by parts because there was only one function. We had to evaluate this complicated u subintegral, and we had to evaluate arctan values. There was a lot of mess to it, but it allowed us to do an integral that we had no idea how to do by Calculus 1 methods.